Hello there guys, welcome back to another epic inexorable maths video. In this video we're looking at separable differential equations, okay? So I'm going to try my best to kind of give some intuition into what a differential equation actually is in this video, and we're going to look at a few examples. Now, what is a separable differential equation? It's just a differential equation that's written in this form. dy dx equals a function of x times a function of y. So as an example, we've got dy dx equals x times e to the power of y. This is a separable differential equation because it's in this form, right? So f of x is x and g of y is e to the power of y, okay? And it's equal to dy dx. So if I said to you, can we solve this? What does that even mean as a question, and how do we do it? So to solve a differential equation means to find the function. So find what y is in terms of x as a function of x, such that in this case, the derivative of that function is the same thing as x multiplied by e to the power of that function. So what function, y, in terms of x, goes in here and works, basically. And that's what we're going to do. Now, the second part of that question, of course, is how do you actually do it? And that's what we're going to do right now. So what I'm going to do is I'm going to give you how to do it in an actual kind of exam setting. And then afterwards, I'm going to give you a slightly more formal way of explaining what we're doing, because a lot of the working out that we're about to do might seem a little bit hocus pocus, okay? It might seem a little bit that doesn't seem very formal. So let's have a look at an example of that. Well, let's actually just do this one and then we'll do some more examples. But yeah, how do you do it? So the method that we're going to use for a separable differential equation to solve it is we're going to use a method called separating the variables, because if it's separable, we should maybe separate something, right? So what you do is you multiply both sides by dx, okay? And immediately, guys, you might have a problem with this, but by the end of this video, I'm going to justify kind of why you're allowed to do that. So I've times both sides by dx, and then I'm going to make sure that I've got all of the x's on one side and all of the y's on the other side. So this is going to be my x side and this is going to be my y side. So I need to get the e to the y to the other side. So I'm going to divide both sides by e to the y. So I'm going to have e to the minus y dy equals x dx, okay? And again, a little bit hocus pocus, if you know what I'm saying, but you're going to integrate both sides just like that. Boom, boom, chuck an integral sign in front. And then you're just going to separately integrate both. So e to the minus y integrates to minus e to the minus y, and x integrates to x squared over 2. Now, technically, they should both have some sort of plus c or plus some arbitrary constant. If you do a plus c on this side and a plus a different arbitrary constant on this side, you can group them all up and you can just have a plus c on one side. Okay, that's totally legit. So that's what we've got there. And then the final step is to get y on its own, because that's the ideal. That's ideally what we want. So let's times both sides by minus 1. So we have e to the minus y equals minus x squared over 2 minus c. And then let's take ln of both sides. That's going to give us minus y equals ln of minus x squared over 2 minus c. And then the final step is to times both sides by minus 1. I'm going to come up here to do that. So if I times both sides by minus 1, I'm going to have y equals minus ln of minus x squared over 2 minus c. And of course, you could put this into a fraction if you want to. So if you want, you can have ln 1 over minus x squared over 2 minus c. And I'm just going to make this look a little bit nicer because I don't really like all these minuses. So I'm just going to rename minus c to like k. So I'm going to say minus c is the same thing as k. So that means I can say y equals the natural log of 1 over k minus x squared over 2, like that. And I think that's the nicest way of writing it. So what we've just done, to be clear, is we've found the function. So we found the function that when you differentiate it, it is the same thing as doing e to the power of it and then timesing it by x, okay? That's what we've just done, and we've used separation of variables, okay? And k is an arbitrary constant. So k can be kind of anything. In reality, there will be limitations on what k can be, or there might be limitations on what k can be. And there's also going to be limitations on what x can be as well. But that is beyond the scope of these kinds of videos, because the nature of solutions to differential equations is something that is incredibly complicated. So we're not going to look at that until far, far later in the future because it gets very messy. So for now, it's all chill. If you're doing something like A-level maths or something, the equivalent, this is enough, this is fine for separation of variables. So this is one example. Let me give you another example. Okay, so here's another one. dy dx equals 1 plus y times 1 minus 2x. Once again, this is clearly in the form dy dx equals function of x times function of y. That's what we've got there. Let's go straight in and do it. So we're going to separate the variables. I'm going to multiply both sides by dx. Again, more on that at the end of the video. So I have 1 plus y, 1 minus 2x dx. If you're wondering what on earth's going on, don't worry, we'll get to that in the end of the video. Okay, let's get all of the y's on the same side as each other. I want to separate those variables, so I'm going to divide both sides by 1 plus y. In this case, I'm going to have 1 over 1 plus y dy equals 1 minus 2x dx. I'm going to whack an integral sign in front, boom, and I'm going to integrate both sides. So what I'm going to get is I'm going to have the natural log of 1 plus y on the left-hand side because that's what that integrates to. And on the right-hand side, I'm going to have x minus x squared plus c. Okay, so again, the plus c doesn't matter which side you put it on, but it makes sense to put it on the side that doesn't have y because now we need to get y on its own, so that would just be an extra step. Cool, so now let's get y on its own. So how should we do that? We need to get rid of the log. That means we should do e to the power of both sides, which I will do here. So I'm going to have 1 plus y is equal to e to the power of x minus x squared plus c, like that. If you're wondering what happened to the absolute value, that is, again, a very complicated question, but just something to bear in mind with all of differential equations is that when you have integration and the natural log of the absolute value of 1 plus y, or the natural log of the absolute value of anything, you can kind of just ignore it. Okay, with differential equations, you can ignore it, but again, the reason is very complicated. So if you're wondering where the absolute values are going when this kind of thing happens, just ignore it for now, and far in the future, you'll be able to appreciate why that's true, but it's very complicated. Okay, then we should take 1 away from both sides. So we've got y equals e to the power of x minus x squared plus c minus 1. And then we can have, let's do this. So let's write this as e to the power of x minus x squared times e to the power of c minus 1. And I've done this because e is a constant and so is c. So e to the c, I can rewrite this as a new variable. And what's pretty common is to do e to the c as capital A. So I can write this as capital A e to the x minus x squared and then minus 1 just on its own like that. Okay, cool. So that's the answer, a e to the x minus x squared and then minus 1. So that is the function that if you were to plug it into this, it would work. Okay, so I've got yet another one for you guys. dy dx equals y tan x. Again, it's in the correct form because it's a function of x times a function of y. So let's go straight in. I'm getting faster now. So let's divide both sides by y. Okay, and then also times both sides by dx. So that's going to give us 1 over y dy equals tan x dx. Again, chuck an integral sign in front of both of them. Integrate. This is going to be the natural log of the absolute value of y. The integral of tan x is not too common, but it's actually the natural log of sec x. Okay, that's what tan x integrates to. And then we've got that plus c, and then we can exponentiate both sides, so e to the power of both sides. So that's going to tell us that y is e to the power of the natural log of sec x plus c. And you've got to be careful because you might want to just ignore the ln's, but there's a plus c there, so you can't actually just ignore. And then what you can do is you can kind of split this up again. So e to the ln sec x plus c, that's just sec x. And so that's e to the ln sec x, that's just sec x, and that's times by e to the c. And again, e to the c, we can rename that to be like a or something. So it's going to be a times sec x. So that's our answer. So we've got y equals a sec x is the answer to that. So once again, if you plug this in, this is the function that satisfies this equation. Okay, so if you do a sec x times tan x, it's the same thing as just differentiating a sec x. Okay, that's what we've just found. Okay, this will be the last one. So dy dx equals 2e to the x minus y. Immediately, it doesn't look like it might be in that form, but it actually is, because we can rewrite it as dy dx equals, this is 2e to the x divided by e to the y, or if you want, that's 2e to the x times e to the minus y. So it is in that form. Okay, you just got to be a bit careful and observant. Okay, now let's just multiply both sides and divide both sides by stuff to separate those variables. Okay, so I'm going to times both sides by dx, and I'm going to need to also times both sides by e to the y. So I'm going to get e to the y dy equals 2e to the x dx. Okay, that's what I end up getting once I've separated my variables. Smack the integral sign in front, integrate both sides. So e to the y is equal to 2e, let me rewrite that, 2e to the x plus c. And once again, you've got to be a bit careful. Take natural logs of both sides here. So that's going to be y equals the natural log of 2e to the x plus c. And again, we've got to be, there's limitations potentially on what x can be and what c can be, etc., etc. But that is the idea. So, obviously 2e to the x plus c has to be positive in order for this to actually make sense. But that's the idea. So again, if you differentiate this function, it is the same as doing 2 times e to the power of x minus this function. Okay, that's what we've just found. Now, as promised, I'm going to now explain why you are allowed to separate the variables. Why are you allowed to multiply both sides of the equation by dx, right? Because I get it, dy dx resembles a fraction, but you've probably heard many times it is and it isn't a fraction. So why can you do that? Also, why can you just chuck an integral sign in front of both sides and call it a day, right? It just seems a little bit, I call it hocus pocus, right? A little bit like, what exactly are you doing? Bit pseudoscience. We don't like that. So I'm going to give you a nice explanation for why this is true. If you don't care, I'll see you in the next video. But yeah, this might be slightly advanced. Hopefully you can follow it. But yeah, I'll spend about 5 minutes explaining this. So basically what I'm going to do is I'm going to show you how to solve a differential equation like this without doing the whole times both sides by dx, divide both sides by g of y. I'm just going to give you an actual explanation for this, and you'll see that the times both sides by dx, divide both sides by g of y argument is a really convenient way of thinking about it, but it's not very mathematical. So here's the idea. In general, we've got dy dx equals f of x times g of y, obviously. Okay, here's the idea. I'm allowed to divide both sides by g of y. That's completely fine because I'm not messing with dy dx. So I've got 1 over g of y times dy dx equals f of x. I've not done anything. As long as g of y isn't 0, then we're fine here, okay? Now, this is the idea. If you differentiate a function of y with respect to x, I'm just going to come over here. Remember that the derivative with respect to x of some function, I'll call it h of y for now. What is this? Using implicit differentiation, you get, it's the derivative of h of y with respect to y times dy dx. This is just implicit differentiation. Hopefully you're happy with that. The reason I'm mentioning this is because this side sort of looks like something that maybe we could think of as having being differentiated implicitly, because there's a function of y here which this 1 over g of y could be the derivative of h of y times dy dx, and then that's equal to f of x. There's no problem there at all. So if I want to integrate both sides, I'm going to now integrate both sides with respect to x. Okay, this is fine because I'm actually going to put the dx on both sides. Okay, so I'm doing this equals this. This is okay. There's no issue with doing this. Okay. And then we just want to look at this because this is fine. This is not a problem, right? We know the integral of f of x, we'll just do that. That's fine. That's computational. This is what we're really focusing on. So what is this? I would like to be able to rewrite this as the derivative of a function of y with respect to x. Okay, what do I mean by that? Well, let's just say that 1 over g of y, I'm just going to rename this to be the derivative of some other function h of y. Okay, this is the idea. Then what I've got is I've basically got the 1 over g of y times dy dx is just the derivative of h of y, right? It's just the derivative of h of y with respect to x, mind you. So this is equal to the integral of the derivative with respect to x of h of y, okay? And remember, y is a function of x, dx, equals the integral of f of x dx, okay? And then this is fine because this is the integral of the derivative of something. So this is just h of y, okay? And then this is whatever the integral of f of x ends up being. And then all of a sudden, you have broken free of all of the derivatives. There's no more derivatives here. So all you've got to do now is integrate f of x, and then you've got to invert whatever h of y is. So if h of y is e to the y, you've got to take natural logs. If h of y is y squared, you've got to square root both sides, whatever that might be. But this is how we've broken out. So just to explain this, because again, this is slightly conceptual, all we've done is we've said, here's our standard, separable differential equation. This is all we've done. And then we've divided both sides by g of y. And we've noticed that actually, this is the derivative of something with respect to x using implicit. And then because of that, we can always, if we're given what g of y is, if we know what it is, which we have done in every single question, we've known what g of y is, we can basically reverse engineer it to work out what differentiated to this, okay? And again, that's h of y, whatever that might be, okay? That is the idea. So maybe here's an example, or here's an idea. Maybe see if you can go back through the questions that we did with this in mind. Try and even do it like this, okay? It's not standard. The standard way of doing it is the way that we've done it, but this is an interesting thing, and I just want to, if it doesn't make sense, don't worry, but I just want to kind of try and formalize this whole times both sides by dx and then just slap an integral sign in front because it's a bit confusing. Anyways, guys, in the next video, we're going to go on to something really cool, which is solving what you call a linear differential equation using an integrating factor, and that's really awesome in my opinion, so stay tuned for that, and I'll see you in the next one. Cheers.
That's just another way to say that I'm the best math rapper in the game today. It might sound vain, but it's just how I feel. And baby, I'm just trying to keep it real. Keep it real. Keep it real. That's right, I was in deep trouble with the law. He threatened government officials countless times and had been arrested even more. Was it them that got him? Was it someone else? Reality is we'll probably never know whose cruel hand that day had dealt. Mathematically analytical but also political. Why do you think our death became so historical? That was